Ready for another deep dive? Today we're really digging into deep learning with chapter 3 of Deep Learning with PyTorch Step-by-Step. And this chapter is all about classification, like teaching computers to sort things.
It's one of those foundational things we ask our computers to do, and this chapter tackles it in a really interesting way. It starts with linear regression.
Oh, yeah, right. I remember that from the last deep dive. It's all about finding the best fit line through a bunch of data points. But I gotta ask, how do you go from drawing a line to actually sorting and categorizing things?
It's a good question, and the chapter breaks it down really well. It's not just about drawing a line and saying everything above this line is this, everything below is that. The model actually figures out the probability of something belonging to one category or the other.
So instead of just saying this is red or this is blue, it's saying there's an 80% chance this is red and a 20% chance it's blue. Okay, I think I see where we're going with this.
Exactly. It's about understanding those odds. And to make this probability magic happen, we need to bring in this thing called the sigmoid function.
Sigmoid function. It sounds kind of musical. What's the deal with that?
Think of it this way. Probabilities are always between 0 and 1 right. But the output of our linear model, those logits the chapter talks about, they can be any number, positive, negative, huge, tiny. The sigmoid function comes in, and it basically takes all of that and squishes it into that nice 0 to 1 range that we need for probabilities.
Okay, so it tames the wild logits and turns them into something we can actually use. That makes sense. But how do we get from probabilities to actually making those classification decisions?
That's where the idea of odds comes in.
Like the odds of winning the lottery are 1 in a million kind of odds.
Yeah, kind of like that. But in our case, it's about the odds of a data point belonging to a certain class. The chapter uses that example of betting on the World Cup. Imagine betting on a team with a 75% chance of winning. That's like 3.1 odds in their favor.
I like that example because it shows how the model is using those probabilities just like we do in real life. Only instead of betting on the World Cup, it's betting on which category a data point belongs to.
Exactly. And just like you have odds in favor and odds against in betting, the model uses probabilities to figure out which way to go.
Okay, so we've got our probabilities, we've got our odds, but then there's this whole log odds ratio thing. That's where I start to get a little fuzzy.
I get it. It sounds a bit intimidating, but it's actually pretty elegant when you think about it. We don't want our model to play favorites right. Like if we're classifying things as red or blue, it shouldn't matter which one we call positive. The model should work the same way either way.
So it's about making sure the model treats both outcomes fairly.
Exactly, and that's where the log odds ratio comes in. It gives us a way to represent those odds symmetrically, so it doesn't matter which class we label as positive, the model stays consistent.
So the log odds ratio keeps things nice and fair. But how do we go from ratios, which could be like any number, to that final answer? Like saying, okay, there's an 80% chance it's this one. Our sigmoid friend comes back in here, really.
Right on. You see, the sigmoid function is specifically designed to work with this log odds ratio.
Yeah.
It takes that ratio, which as you said could be positive, negative, big, small, whatever, and it squishes it down really elegantly into a value between 0 and 1, which is exactly what we need for a probability.
So it's like the sigmoid takes this kind of abstract mathematical thing, the log odds ratio, and makes it something we can actually understand.
Yeah, exactly.
Yeah.
And once we have that probability, we can start making decisions. This is where the chapter brings in the idea of a decision boundary.
Decision boundary. Okay, that sounds kind of intense, like a force field or something.
Think of it like this. Imagine all your data points, all those red and blue dots the book uses, all scattered out on a graph. The decision boundary is basically a line that we draw through those points to divide them into two groups.
So it's like we're sorting our Legos again, but the decision boundary is the thing that separates the red ones from the blue ones. And the sigmoid function helps us figure out where to draw that line.
Exactly. And here's where it gets interesting. The easier it is to actually separate your data, like if you can draw a line and all the red dots are on one side and all the blue dots are on the other, the better your model is going to be.
Right, that makes sense. It's way easier to sort Legos if they're already kind of pre-sorted into piles. So a good decision boundary, a good line, should make a clean cut between the data.
Exactly. But of course, in real life, it's not always so clear-cut. Sometimes your model's going to misclassify some things.
Right, like some red Legos might end up in with the blue ones, and that's where the confusion matrix comes in. To be honest, that name always throws me off.
It's a little dramatic, I know. Just think of it as a way to see how well your model did, like a report card for how well it classified things.
Okay, so instead of grades, it's got
It shows you how many things your model got right, how many it got wrong, like how many red dots it thought were blue, that sort of thing.
So it's not just about getting it right or wrong, but understanding what kinds of mistakes the model is making.
Yeah, exactly. And this is really cool. You can actually adjust how picky your model is. It's called adjusting the classification threshold.
Oh, so it's like changing how strict your spam filter is so you can catch more junk mail without accidentally blocking important stuff.
Exactly. It's about finding the sweet spot.
Yeah.
And that's where those ROC and precision recall curves come in handy. You ever have one of those situations where a false positive is like way worse than a false negative?
Totally. Like with a medical test, getting a false negative could be a much bigger deal than a false positive.
Exactly. Those curves let us see those trade-offs. They're like a detailed report card for your model. They don't just tell you a grade. They show you how it performs at different levels of pickiness.
So we've got these curves, these like visual snapshots of how our model is doing. But how do we actually use them to make decisions about our model? Like seeing a curve is one thing, but how do we know what settings to use?
That's where we use something called area under the curve, or AUC for short. It basically boils down the information from those ROC and precision recall curves into a single number, kind of like giving your model an overall score. The higher the AUC, the better it's doing at balancing those trade-offs between different types of errors.
So a high AUC means we found that sweet spot, right? Like having a spam filter that's really good at catching junk without blocking the important stuff.
Exactly. And luckily, the chapter shows you how to calculate this AUC score using a tool called scikit-learn. It's like a specialized calculator just for evaluating machine learning models.
So now we got all the pieces of the puzzle. We start with linear regression, then bring in the sigmoid function, add in the log odds ratio to keep things fair, visualize our decision boundary, analyze those confusion matrices, and finally we check our model's report card by looking at the AUC.
And the best part is, this chapter doesn't just throw all these concepts at you and leave you hanging. It walks you through the actual code, showing you how to implement everything in PyTorch.
Yeah, it even shows you how to make those decision boundaries visual. Remember those contour plots we talked about last time? Now we're using them to see how our model is dividing up the data. Pretty cool.
It really helps make those concepts click, doesn't it? Speaking of which, did you catch that part about the validation loss sometimes being lower than the training loss?
Yeah, that seemed a bit weird to me at first. Shouldn't the model be better at classifying data it's already seen during training?
You'd think so, right?
Mm-hmm.
But it all goes back to that idea of how separable the data is. Sometimes, just by chance, the validation set might be a bit easier to separate cleanly than the training set.
So it's not necessarily a bad thing, just kind of a quirk of the data.
Yeah, exactly. And remember, just like with anything else, practice makes perfect. The more you work with these concepts, the sigmoid function, the log odds ratio, decision boundaries, confusion matrices, ROC, and precision recall curves, the better you'll get at building models that can tackle real-world problems.
So there you have it. We did it. We took a deep dive into classification with PyTorch. We covered a ton of ground today, but hopefully you're feeling ready to dive into this chapter and start experimenting yourself.
Absolutely. And remember, if you ever need a refresher, we're always here to help. Just revisit this deep dive and we'll walk through it all again. Until next time, happy learning.
Happy learning.